Again, good morning. You're going to see me for almost 1 hour, 2 presentations in a row. So this is a work that I've done together with my colleagues in Denmark from University of Aalborg. And the main problem that we try to solve here is computational offloading. Of course, we did not reinvent the wheel. We use existing technologies. And in this work, in this paper, I want to present a use case where we practically applied some existing technologies to a simple use case. So this is mainly, let's say, master project work. What's the context? We have makerspaces. You know what are those makerspaces? Those places where people can go and do some activities like 3D printing and whatever. And now in Denmark, there is the need to have those makers so that they want to do some complex 3D modeling. So they want to prepare their 3D models before printing. And those need a lot of rendering, a lot of pre-processing, let's say a couple of hours of execution, sometimes even 8-10 hours, depending on how complex they are. There is another issue. They don't want to send it to the cloud for whatever privacy reasons, or simply they are not skilled enough. Most of the time, they are simply designers or they are maybe normal persons. I mean, the average person without IT skills, without software engineering skills, that they go there. They just learn the technology with these tools like SketchUp and those very easy tools. They know how to make a cube. They know how to make something way more complex, but then they don't know how to, compute on Amazon or compute it somewhere else. So they just want something simple with their phone, click and run. So the Makerspace decided, why don't we provide computational power to those users? But the main problem was that in Denmark, they need to shut down during the closing time. And legally, they need to shut down everything, including the servers. Now, don't ask me why. This is just the law. So in that case, they have to shut down the machines. So also the computation, of course, need to be interrupted. So how does this system work? They wanted to have a system with a phone. They had an app on the phone where they're able to design their tools, their prototype. It's pretty complex, in my opinion, just to make this 3D modeling. And once the 3D modeling is done, then they need to submit the job for the pre-process, this checking. To give you an idea, if they want to build like this glass with 3D modeling, they need to be sure that this is completely waterproof. So that means that all the shell is completely solid and there are no holes in any part of the glass that can penetrate water. So that means, imagine when you print it, you print just the external layer, just the outer shell. And you need to be sure that there is no water dripping inside every thin layer. And this computation can take some time, can be more complex. So what we wanted to do was to provide them this computational power, shutting down the system, and enabling them to continue when the system is shut down. So imagine someone, let's say at 6 p.m. they shut down. I don't remember exactly the time. I'm just giving an example. We shut down at 6 p.m. the machines. So when it's, let's say, 5 minutes to 6 p.m., we don't want to tell the users, no, please don't do that. Don't send my job. Or we don't want to tell the users in the evening, please don't do your 3D modeling, because most of the people will do it in the evening. So we want to have the possibility to run it as much as possible, and then stop, checkpointing, and send it back to the user, the partially computed data. Again, some of you say, why do we need to send it back? Why I can't keep it on the server? Again, because for whatever legal reason, they need to shut down the machine and wipe it out, everything. So every morning, we start from a fresh state of all the machines. So this is, again, an example that can be obviously translated to multiple use cases. It's not just for this specific. So what did they wanted to do? This simple app that enabled to upload the job to the system, run and compute everything on edge devices and on this local computational system. Of course, authenticate all this basic user loading system. I don't want to bother you with all the technical details of that. And to have the user interface, of course. Obviously, the system needs to be able to detect also near users. Why? Because when they enroll it, if they don't have enough computational power on their mobile phone, we want to enable also other phones of other users to run part of their computation. Of course, if they allow for privacy and whatever reason, and obviously the classical notification system. So it's not an extremely complex task. Now, I want to show you first what's the main solution. So the idea is that we have everything developed with Docker containers. So we have the basic Docker container that everything is running on servers and on different workers. The idea is that we execute the task. We save the results on a result file, but if the result is not yet ready, we are ready to periodically make checkpoints. This helps also in case of energy interruptions. So every few seconds, we simply make a checkpoint of Docker containers. If something happened, we just lost the very few seconds of execution. And then when the job is finished, then in that case, we don't checkpoint anymore. We finish, we send the results to the user, and that's all. This enables, if we have this checkpoint, eventually to save the checkpoint to the disk, to the worker, or send it back to the original user, to the phone of the user for the execution. Why it's not going? Yes. So how is it simply implemented? So we wanted to have proof of concept and to make it very easy to show to the students, let's say, the technical functionality. We make the first implementation with Raspberry Pis. Then the second version, the one, I mean, after submitting the paper, they also implemented it with the new Jetson. So they use Jetson Orin, and they use also other NVIDIA, they use just a workstation with some NVIDIA system. But for the sake of the paper, when we submitted the paper, they were implementing just with Raspberries. You know, it's easy to hand out the students like 10 Raspberries is cheaper. I don't want to give 3,000 euros Jetson Orin, and maybe 10 of them to the students if they break it, or if sometimes lose them for whatever reason. So what is interesting is that we wanted to have the client talking directly with the edge device and not always going to the proxy. So the idea is that the client was contacting the backend was giving the information from the proxy, and then the client was able to have a direct communication to in this case, to the Raspberry Pi, so to the edge device. So we set up very, very easy configuration in the beginning with a server that it was running on Docker, on a Raspberry Pi. Now, of course, it's not anymore on a Raspberry Pi. Now this is on a simple Dell Blade machine. I mean, it makes more sense, of course. And the worker was also Raspberry Pi. Now we have this fleet of Jetson Orin running those devices. And then we had one Android mobile device who was sending all the different information. Everything is communicating using FTP server, so the data is transferred using FTP. This was a simplification, but it works pretty well. Still, we have authentication, we have everything we need. The interesting aspect that we wanted to add was the energy meter, because from our point of view, especially because we are working in a European project, national project about energy saving in edge, we add an energy meter to every single device. And for this purpose, when we run the different computation, we wanted, for the next paper that's not yet published, to monitor the energy of every single task running on every single devices. And we run it one single container per device, just because we wanted to be able to monitor this energy. I mean, more details on the energy, if you're interested, of course, can be said later. This was not part of this paper. So this is a simple interface that the students develop. So they are able to have this kind of jobs, the jobs queue. They have different location of Makerspace where they can go, where they can run it. What is interesting is that using this approach, users can technically checkpoint their work at any time. So it is not positive only for shutting down the Makerspace. It is also positive for, oh, something happened. Yeah. I would say this approach is not only useful, of course, for this Makerspace that they need to shut down, but it's useful for any kind of system that need to offload the computation from a device to another device. What we wanted to see is how often we have problems, how often we occur some issues in the checkpoint where the system cannot restore again. So we run a kind of small experiment to see, to execute a lot of different checkpoints on different containers and see how often this breaks. And the result is extremely, extremely low. So we see that is extremely reliable. We can easily checkpoint Docker using simple Docker checkpoint functionalities and transfer. The only problem is timing. It takes time. The bigger is the Docker container, the longer it takes to checkpoint. One recommendation that we realize is try to keep the Docker as lighter as possible. And this is generic for every let's say, cloud-native system, even for serverless functions. And example, the students, they develop a system importing every type of Java libraries they were kind of needing. But if there is a library that is lightweight, if there is a library that you don't need it, you don't need to import it, because then it is imported in Docker and then it's growing up a lot. And this was summing up and having like a chain of effect. So, in conclusion, let's say this was just a proof of concept for the workshop where we wanted to see how reliable was Docker checkpointing for edge offloading. It was just the beginning of this journey. It was the early stage of one of our national project and an European project. We are planning, of course, to extend it a bit more, and we are planning to make a comparison between Docker and other containerization technologies, especially with unikernels and other containerization that might be more lightweight or might be faster. I can already tell you, again, not part of this paper, I want to spoiler a little bit, that Docker takes a huge amount of energy to checkpoint. So it's a waste of energy. Every time we checkpoint, we wasted energy. And if you do it periodically, like we did, you burn useless energy. Of course, you can have some predictive way, you can have better system to checkpoint, but other type of containers might be a little bit better. I mean, they are trying, of course, to upload, to implement new features, to add GPU support. We still don't know if we have GPU system, the checkpointing should be identical. But how about restoring the computation on the GPU? Will this increase the overhead, checkpoint and restore overhead? Because it's not everything on GPU, you know, reallocating everything, still not clear. And of course, we want to support more workload and also federated learning. For some reason, I need to press several times to go to the last one. It was like a thank you slide. Thank you.
Thank you, Davide, for this presentation, which is an ideal presentation. If somebody reads your presentation and then reads the paper, he will be able, believe me, to understand the paper, because we have presented the most important features from the work. Are there any questions?
Yes.
Yes, Professor, that's for you.
Let's take it down. In the original. Yeah. Okay, so thank you, Davide. In the original motivation, one of the concerns was that people might not be willing to upload whatever processes they have started already to the cloud for security and privacy reasons. Mm-hmm. But then we resort to the communication among nodes like Raspberry devices, and especially over FTP. Yeah. Would that be a more secure solution?
Well, I'm not sure what is the best solution. Probably FTP over SSH would be the most secure solution. I'm not a security expert from this point of view. I can't compare security protocol. Okay. No.
I'm just thinking whether the problem has been delegated to another layer, which by definition has its own vulnerability.
No. I mean, from this very specific use case, the problem was more a mindset. You know, people, especially not computer scientists, they trust more a physical place where they can go there and they can talk with a person and they say, I'm sending my computation to you, and not to the cloud that is like a god who you don't really know where it is. Obviously, we are talking about non-computer scientist users. We are talking with people with different background that might have different belief, of course.
All right, thank you.
Thank you. I'm a little bit confused about the computational demands, because you started saying that it is 10 hours, sometimes a few hours of work, then really with Raspberry Pi, but Raspberry Pi was for the student, then you did it with some blade. So this, the actual rendering, the actually 3D modeling and checking task, how long would it take and on what hardware? So what is the actual target hardware for these Makerspaces?
The actual target hardware is GPU, of course, and that's why we set up those NVIDIA Orin, mainly NVIDIA Orin. We have just one workstation with an RTX. I don't remember the number, but one of the most recent ones. And the actual job depends on how complex is the structure. So if you take, like, if you want to render this glass, it's a matter of few seconds. But if you want to render like this projector with all these tiny cuts and maybe some other technical details, well, it can be even 10 hours. So that means it's not going to be executed in one day, because it's less than 10 hours, the opening hours.
If the actual gaming, people if you really something bad for you use and something really powerful.
Can be compared to a gaming PC. Yeah. No, it's comparable to a gaming PC. Well, if you take like a Jetson Orin, more or less, it's a gaming PC, more or less.
If I understood well, all the energy monitoring is done by hardware devices. And how far have you go on disclosing every single element on the computing in terms of the energy consumption? Have you?
This is going to be part of the next paper, but I want to give you some spoiler. So we are actually monitoring, we are using some physical device, let's say physical energy meters, to monitor the consumption, and we connect it directly to the DC side. I mean, directly to the power side of the devices. Of course, we are not monitoring the single component. We are just monitoring, for example, how much energy is drawn by, for example, the Jetson Nano or the Raspberry Pi. I don't know then how much is taken from GPU, from CPU, from memory. This is kind of too much.
Have you plans to use Kepler or Cassandra to get inside the computing resources consumption as well?
Might be an option. Yeah, I mean, I think we are first starting try to understand what's the overall consumption and make comparison, especially between containerization technologies. After that, we might even go in deep. I mean, this might be an interesting discussion later on.
Yeah, for sure.
Let's talk about it.
David.
Question, just a final one by my side. Do you plan to adopt this model in some future, let's say, developments like the ones we have described in the paper in the municipalities or the research institute?
Not at the moment. I mean, this example was mainly to check. I mean, the real reason of running this study, it was mainly to see how reliable was Docker checkpointing system. And then we applied in that use case because we had the need, and actually we had the funding from Denmark side. But the real reason was checkpointing.